Picture this, a thin sheath, warm to the touch, catching body heat and motion, quietly turning intimacy into tiny sparks of power. In the lab, I call it the energy condom. Not a fantasy, but a design problem that sits at the intersection of energy engineering, material science, and sexual health. Think of it as a little energy factory that must stay a perfect barrier. I walk in with a cup of coffee and a roll of latex. Across the bench, a colleague from reproductive health unrolls a microstructured film. We argue like good scientists, how to harvest energy without breaking the barrier. The laugh is short, the challenge is real. Friction makes charge, heat makes voltage, pressure makes current. Each is a source we can tap. If we respect safety first, triboelectric nanogenerators are seductive. 2 layers with different electron affinities slide. Electrons jump, and a pulse appears. Micropattern the inner surface to increase contact area. Make a textured outer surface that amplifies relative motion. But here comes the trade-off. Lubricants reduce friction. That slippery kiss that makes users comfortable also kills the triboelectric signal. So we design selective roughness, channels that keep lubricant away from active patches, or isolated pockets of dry contact that never touch bodily fluids, all while ensuring no compromise to barrier performance. Thermoelectric films are quieter. A thin Seebeck element across a tiny temperature gradient, skin versus ambient, produces continuous microvolts. Thin films minimize thermal resistance. A sandwich of conductive polymers and elastomers captures heat without stiffness. For math is humble. Microwatts, enough to power low-energy sensors, not Wi-Fi. Combine small harvesters and energy-efficient electronics, and suddenly you can log temperature, detect slippage events, or validate correct use for clinical study. Piezoelectric threads woven into elastic backs convert pressure pulses into spike, but embedding stiff crystals into a flexible membrane is dangerous if you stiffen the film or create stress concentrator. So the engineering sweet spot is low modulus composites, percolating networks of conductive polymers below the percolation threshold to keep elasticity, and encapsulation layers that preserve impermeability. Material choice matters. Latex offers excellent elasticity and established safety standards like ISO 4074. Polyurethane is thinner and less allergenic, but behaves differently under stress. New elastomers promise biodegradability, great for life cycle impact, but need rigorous burst and permeability testing before any human use. Then there's the dark side of clever coating. Graphene sheets and silver nanoparticles conduct beautifully, but they must not leach or pierce. We simulate mechanical cycles. Fatigue, inflation, torsion. We test for micro tears, gas transmission, tensile strength, and biocompatibility. Every conductive path must be sealed from fluids, and the electronics, ultra-low power ASIC, flash memory, and secure protocols must be scrupulously anonymized. Data ownership is ethical engineering. Picture an experiment, a prototype with a tiny LED that pulses with each pressure event. It's playful, hinting at sensation. But its true power is data for researchers' timing. Force curves, thermal maps, a new window into human contact without cameras or invasive sensors. Imagine using that data to improve contraceptive counseling, to study lubricant interaction in real-world conditions, or to model failure modes more accurately. The story ends, not with a gadget, but with questions. How do we balance harvest efficiency with lubricity? Can biodegradable conductors match latex's toughness? What ethical framework will govern intimate data? For those of us who love both energy flows and human flows, this is irresistible, an engineering problem that respects pleasure, privacy, and protection. If you want to play with heat, charge, and elasticity in a safe, rigorous way, roll up your sleeves. The lab bench is waiting, and the next breakthrough might start with a tiny spark under a thin film.